Okay, good morning. So in the previous lecture, we have been discussing about different psychometric processes, some of which were pure heating. Then we also attempted towards humidification. And while we were doing humidification, we found that achieving pure humidification is a challenging process because we have to maintain the enthalpy of the water vapor which we are seeding into the moist air equal to that of enthalpy of moist air. Then only we will be able to achieve the pure humidification. It is through other means, seeding of water actually, uh, through the artificial means is actually challenging to achieve. So that's why we majorly found that pure humidification could be resulted due to infiltration. So infiltration is the major source of pure humidification. Whenever artificially we will be dealing actually, then either there will be humidification and heating or humidification and cooling. Okay, so that will be happening. Now, then later on we started discussion on combined heating and humidification process. In case of combined heating and humidification, we have heater also and we have some water spray also. Okay, so when I am doing heating, it means temperature must increase. So if I am at state point 1, my final point 2 should be such that temperature is increasing. And second thing is when I am having humidification also, so W1 will be less in comparison to final humidity. So that's why I will be getting inclined line something like this. Okay. Now this inclined line can be converted into a triangle. So this is the overall process which is happening in this control volume, but it can be splitted into two parts. It can be one horizontal line from 1 to 3, which will be representing that humidity is constant, only heating is being done. So it is a sensible heating portion, and the process from 3 to 2, which is a pure humidification process, it will be only representing the latent heat load on the system. Okay, so I can say that 1 to 2 is the total heat load, out of which 1 to 3 represents the sensible heat load and 3 to 2 represents the pure humidification, or pure humidification means latent load. So that is the reason I wrote Q12 equal to Q13 plus Q32, and then Qt is equal to Qs plus QL, because 13 is Qs and this is QL. Now from the previous approximate equations, why I am calling these approximate equations? Because we have made certain assumptions that 1.88 is negligible, or many other small assumptions we have made while we have come to these equations. So that's why these are nothing but the approximate equation. So approximate equation for sensible portion will be 0.0204 VA into T3 minus T1, and for latent load it will be 50 V dot A into W2 minus W3. And in terms of enthalpy, if I am plotting the process directly on the psychometric chart, then after locating state points 1, 2 and 3, I can directly measure the enthalpy values I can obtain directly from the chart itself. Okay, so after obtaining the enthalpy values, I can write the actual equation. Is this one clear? Now I told you one important point, sensible heat factor. Okay, so sensible heat factor is typically given as Qs by Qs plus Ql, which is sensible load divided by total load. So total load was H2 minus H1. If I try to write in terms of approximate equation, it becomes 0.0204 VA into T3 minus T1 divided by sensible plus latent load. Okay, so if I do little bit algebraic manipulations of this equation, I can divide throughout by this term in the numerator. So then I will be getting 1 divided by 1 plus 50 by 0.0204. Okay, V dot A will be cancelling out, and here I will be getting W2 minus W3 divided by T3 minus T1. Is this point clear? Now can you tell me, first you tell me what is the value of 50 by 0.0204? How much it is? Please tell me. Two four five zero. Okay. Then W2 minus W3 divided by T3 minus T1. What is this? W2 minus W3. This distance which is perpendicular for this triangle, and this will be becoming T3 minus T1 is base. So it means it will be giving 10 of 10 of this theta. Okay. So I can write it 10 theta. Is this point clear? So it means sensible heat factor is nothing but a function of theta. Okay, and ultimately it is representing the slope on the psychometric chart. That is the reason I was explaining you the process, that usually in a psychometric chart we have this type of scale also. Okay, which is called as sensible heat factor scale. Is this one clear? So this sensible heat factor scale, what it does, here value of SHF is given. So what I can do, there can be a process specified in such a way that this is the initial condition of the air, and the sensible heat factor for the process is say 0.5 or 0.6. Okay. So if that is the case, then how I can draw this final state? How I can draw the inclined line? Is this one clear? So for that purpose, what we need to do, corresponding to the scale of sensible heat factor, I need to first locate the value, whatever the given value, for example, 0.5. Clear? And after that, from 0.5 value to, what is this? Alignment circle. I will be drawing a straight line in between this point and alignment circle. Is this one clear? And after that, because point 1 I have already located somewhere, I will be moving a line parallel to this line. Okay, so a parallel to this line I will be passing through point 1. So that line will be representing actually path of the process. And of course, where the process will be ending, one of the parameter, whether temperature or humidity, must be specified. Then we will be able to tell that on this parallel line where we have to stop the process. Is this point clear? All are clear with this idea of using the sensible heat factor scale? What is its utility? Why it is given in the psychometric chart? Other than that, in some psychometric charts, let me also clarify this point. You will be finding in some psychometric charts that this type of sensible heat factor scale is not there. But what they have, somewhere over here, they have a, with reference to this point, some protector like scale like this. Okay. So in this scale, they have marked again the values of sensible heat factor. So in this case, what we need to do, corresponding to simply parallel to this, we need to draw the line over here. Is this one clear? And of course, these slopes will be function. So this side will be applicable for dehumidification processes, and this side will be applicable for humidification processes. Is this one clear? So this type of sensible heat factor scale also you may find in some of the psychometric charts. In some psychometric chart you will be finding here, and in some psychometric charts you will be finding it here. Okay. So if you refer to different books, there can be different format of psychometric charts. The only major difference, rest of the things you will be finding almost the same. The major difference you will be finding in only the sensible heat factor scale. Is this one clear? Anyone is having any doubt about this? Okay. After this, let's now talk about one simple process, which is adiabatic mixing of moist air. Why it is important to study adiabatic mixing of moist air? You tell me. See, this is the room. Okay. So in this room, I am doing the processing of the air. What will be happening? If I just keep on circulating this air only, after some time this air quality will not be breathable. Okay. So what I need to do, I need to control the quality of air. For controlling the quality of air, what I will be doing? Some amount of air I will be adding from outside and I will be mixing with this air so that dilution can happen. So it means that when we typically work with the air conditioning system, in order to maintain the quality of the air, we need to allow some outdoor air to get mixed with the room. Okay, so that's why to study that, basically what we are doing kind of adiabatic mixing between the two streams. Okay, so situation is very simple. Say this was my main duct which was carrying some moist air at flow rate m dot a1 and enthalpy h1, humidity w1. Then I have provided some uh, damper over here, and when I opened this damper, then say some another air stream m dot a2 has entered whose humidity was w2 and enthalpy was h2. Okay, and while these two will be mixing, these have resulted in flow rate of m dot a3, humidity was W3 and enthalpy was H3. And this process, if I draw the control volume, I will be saying that there is no heat interaction across the boundaries of the duct. Okay. So in this way, what will be happening? If I write the mass balance for the air, then m dot a1 plus m dot a2 will be becoming equal to m dot a3. If I write mass balance of water vapor, what I will be getting? Please tell me. Mass of water vapor in incoming air is m dot a1 into w1. Mass of water vapor in m dot a2 into w2 equal to m dot a3 into w3. If I replace m dot a3 with this, then what I will be getting? M dot a1 plus m dot a2 into w3. From here, I will be getting that m dot a1 into w1 minus w3 will be equal to m dot a2 into w3 minus w2. Okay, and simply I will be getting that m dot a1 by m dot a2 is equal to w3 minus w2 divided by w1 minus w3. Is this point clear? What it means? It means that if I am on psychometric chart, and say this is my stream 1, this is stream 2. When these two will be mixing, ultimately I will be getting some point 3. Okay, and how far and how close is point 3 from state 1, that will depend upon their mass fractions. You can simply see what is W3 minus W2, this distance. What is W1 minus W3, this distance. And you see this distance is proportional to this flow rate by this flow rate. So it's very simple that if this flow rate is more, then I will be coming more towards 0.1, and if it is 2 is more, then I will be going more towards 3. Is this one clear? So the length segments, basically whatever the length segments I am getting on psychometric chart, these length segments are dependent upon what? These are dependent upon the ratio of mass flow rates which we are considering during the adiabatic mixing. Similar will be true for enthalpy equation also, because what will be my enthalpy equation? M dot A1 H1 plus when you will be doing replacement, simply you will be getting m dot A1 by m dot A2 is equal to H3 minus H2 divided by H1 minus H3. Is this part clear? Is this part clear? Anyone is having any doubt about this?
सर हम बाहर से जब भी मतलब ऐड कर रहे हैं एयर का क्वालिटी ठीक होता है सर.
Mostly it is done from the practical perspective. I am telling.
मतलब सर जैसे ऐड कर रहे हैं तो सेकंड वाली ऐड करें मतलब Ma2 तो उसकी जैसे रिलेटिव ह्यूमिडिटी ज़्यादा ही
Yes.
WL तो कम रखनी चाहिए ना सर तो
Sorry.
कम रखनी चाहिए ना सर WL ताकि मॉइस्चर कम रहे कंफर्ट
That is why, but see, our aim will be to maintain the comfortable situation as per the indoor condition. So means in general, if you are thinking from practical perspective, point 1 is corresponding to indoor air. Indoor air means room air. Point 2 is corresponding to outdoor air, like ambient air. Now if I have some AC in for within the room which is controlling the humidity, outside the room of course humidity will be more. So but in order to avoid the concentration of more concentration of CO2 in the indoor air, I have to add certain amount of outdoor air. Okay, so that is the reason when I have added outdoor air, the overall humidity, it is not exactly equal to outdoor air nor it is equal to indoor air. So total humidity has reached to some point 3. Now after this mixing, I need to have some cooling coil which can further decrease humidity from 3 to 1. Is this point clear? So it means that this mixing of ambient air actually creates additional load on the air conditioning apparatus. Okay. So how it creates additional load, you need not to worry now. Right now I am only explaining the basic processes. After this, we will be doing the design of air conditioning system. Okay, so if outdoor condition is given, indoor condition is given, then how much there will be total load on the apparatus, how much will be latent load on the apparatus, how much will be sensible load, all these things we will be actually doing subsequently. Okay, is this one clear? So all are clear about this point? Now let me complicate this process. How I can complicate it? Let me consider this is my state 1, this is my state 2. What I am having? One I am having very cold stream and other I am having very hot stream with very high humidity and cold stream is having very low humidity. When I will be mixing these two, my straight line will be like this. Straight line is like this. So where my point is coming? Point 3 is coming outside the saturation curve. What it means? What will be happening here? Please tell me what will be the state? What I will be getting? See, I am crossing the 100% saturation state. What it means? It means that water content is even more than saturated state. But can moist air hold water content above than saturated state? No. So what will happen? I will be getting two components. Let me again draw this process and explain to you in detail. So this is point 3. Okay. So it means when I am mixing very hot air and with high humidity with very cold air at very low humidity, I am getting some final mixing state which is going outside the 100% saturation line, which typically cannot happen because moist air is having certain capacity to hold the moisture. So in this case, what will be happening? I will be getting actually some point on the saturated curve, 0.4, corresponding to which I will be getting final moist air. I will be getting final moist air which is 100% saturated. But the water volume or water mass is more than the mass which is handled by that air. So what will be happening? Some amount of water now will be present in the moist air in the form of very fine liquid droplets, which typically are nothing but the fog droplets. All are clear with this point? Is this point clear or not? So what I will be having then? Mass balance for dry air will be m dot A1 plus m dot A2 equal to m dot A3. This is the mass balance for the dry air. Mass balance for water vapor will be m dot A1 into W1 plus m dot A2 into W2. Now I am saying mass balance for, okay, for total water. First let me write for total water. It must be equal to m dot A3 into W3. But this W3 state is at present practically seems not feasible. Okay. Then what I can do? I can write now the mass balance of only water vapor. So if I write mass balance of water vapor, I can say that m dot A1 into W1 plus m dot A2 into W2 equal to m dot A3, but instead of 0.3 it is with which state? State 4, because in vapor form only maximum saturated content can be there, so it will be with W4. Is this point clear? It means that there is some mass of water vapor. How much? Here you can see the mass of water in the form of liquid droplet will be m dot A3 into W3 is my total water mass, and m dot A3 into W4 is the vapor mass. So total water mass minus vapor mass will be becoming m dot A into W3 minus W4. So this much amount of flow rate I will be getting in the form of fine liquid droplets. And these liquid droplets, whenever are present in the moist air, these are nothing but called fog droplets. Okay. Is this point clear or not? All are clear with this point? So it means that if you have extremely high humid environment, by this process you can actually, what you can produce? You can produce fog. And whenever multiple fog droplets will be, whenever your environment will be significantly seeded with all these fog droplets, there will be nothing but your clouds. And when in the clouds, because of turbulent mixing, these very fine tiny droplets will be joining with each other and forming the larger size droplets which can fall in downward direction, then it will be becoming rain. Okay. Is this one clear? Point is clear. What typically happens? We see that evaporation happens from the sea. So whenever that evaporation is happening, it is carrying very fine submicron droplets. Okay, in the range of 1 to 20 micrometer diameter, liquid droplets. Because of their very light density, very small size, these gets carried away with the hot air. When these are going away with the hot air, and finally at certain height, these actually, we will be finding that significant portion of the droplets is accumulated at certain portions. Then these are nothing but clouds. Then within the clouds, what happens? So many turbulent phenomena happen. Because of turbulence, what happens then? Mixing of the droplets happens. And this mixing leads to formation of large size droplets, and then ultimately the rain droplets produces. Okay. So this type of situation, I am not saying that maybe, but this type of sequence of processes can be even used to achieve the artificial rainfall. Nowadays it is again in very news. Huh? Have you seen daily news that IIT Kanpur is trying to do some artificial? So what they are doing? They are not basically doing the entire process. What they are doing, already whatever the clouds are there, in these clouds actually
they are spraying salts.
yes, certain salts, so that accumulation of fine submicron droplets can take place to form large size droplets, and which can fall in the form of rain droplets. Okay. Is this point clear? So this is the mass of water vapor which this is the mass of water which I will be having in the form of fine liquid droplets, which are nothing but fog droplets. Okay. So in this process, if you write the enthalpy balance, then m dot A3 will be having enthalpy H3. Basically what I will be getting, m dot A1 into H1 plus m dot A2 into H2 equal to m dot A3 into H3. Now this m dot A3 into H3 can be splitted into two portions. It can be written as m dot A3 moist air at state 4 H4 plus additionally what it has, m dot W into HF4. What is H4? H4 is enthalpy of moist air in the gaseous phase. Gaseous phase. H4 will be basically 1.005 T4 plus W4 into 2500 1.88 T4. Okay, so that is H4, but HF4 is also there. What is HF4? HF4 is enthalpy of water in liquid state. Because the fog droplets are present in which state? Moist air is containing moisture in vapor phase, but fog droplets are contained in the liquid state. So let me write it. M dot A3 will be cancelling out. H3 equal to H4 plus W3 minus W4 into HF4. Okay, so this is the equation for this process. Now, can you determine state 4? In graph, I have simply located some random point. But in order to exactly locate this point, we must have some mathematical basis. At present, what I am finding is that we have only a single equation. In this equation, what are unknowns? H3 I can determine by directly using this mixing. H4 is unknown, W4 is unknown, and HF4 is also unknown. So what I need to do now? Iterative method. Okay. I will be assuming some temperature for 0.4. If I assume some temperature for 0.4, that I know that 0.4 is only at the saturated state. Then corresponding to that T4 temperature, I can calculate value of W4. So at T4 I will be getting W4. I will be also getting H4. I will be also getting HF4 from the steam table at temperature T4. Then I will be substituting in this equation and I will check that if it is satisfying the equation or not. If it is not satisfying, then again I need to change the value of temperature. Okay. So how this iterative process is to be executed, that we will try to see with the help of a numerical problem. Is this point clear? So we will do a numerical problem maybe today or tomorrow, where we'll try to execute this iterative process. All are clear with this point or not? Is this point clear?
Okay, now how many of you have practiced numerical problems? Practiced? No? Okay, let us start today some numerical problems on psychometry. We have moist air which is entering an insulated duct at the rate of 10 kg of dry air per minute. So, mass flow rate is given in the form of dry air and it is given as 10 kga per minute. So, moist air is entering a insulated duct. Please, I am not writing all the details, I am just writing only the numbers over here. So, all of you please note down the statement that moist air is entering an insulated duct with mass flow rate of 10 kga per minute at 20 degrees Celsius, 50% RH, 20 degrees Celsius, 50% RH and standard atmospheric pressure, PATM. Pressure is standard atmospheric pressure. If it is heated by a heater of 1 kilowatt capacity, it means we have a heater of how much capacity? 1 kilowatt capacity. It's then what we need to do? We need to determine the outlet state. We have to tell outlet state. Very simple problem. Very simple problem. It is a blower problem. Okay. So air is taken from one side in the blower, then blower rod is actually heating at the rate of 1 kilowatt and then you are getting hot air. So you have to tell what will be the temperature, humidity, etc. of the hot air. Outlet state you need to determine. Yes, tell me, how will you be doing this? You have to tell me the process now. And let me also tell you, though now you may ask me that please give us psychometric chart. Okay, that you want to locate state 20 degrees Celsius and 50% RH and you will be calculating value of enthalpy or W. W means specific humidity, etc. Okay, but psychometric, it can, this problem, of course, if I have psychometric chart, I can solve it with very ease, but it can, sorry, it can also be done without psychometric chart using the relations which we have studied. Relative humidity will be same or specific humidity will be same? W will be same because we do not have any addition and removal of water. Okay, how we can do this? Please tell me. We have been studying these basic concepts for many lectures now. Sorry? How to determine W over here? Tell me. What we need to do? We need to calculate W, na? RH is given, temperature is given. How I can calculate W? Let me write some relations. I know W is equal to 0.622 into PW upon P minus PW. Correct? How I can calculate PW? What is PW? Partial pressure of water vapor. Is the partial pressure of water vapor related to vapor pressure through some relation? What is the formula for relative humidity, which typically is given by symbol phi? In terms of mass, but later on when we reduce it in terms of pressure, it is PW upon PWS. So it means PW can be replaced with phi into PWS. So 0.622 phi into PWS divided by P minus phi into PWS. What is PWS? Vapor pressure. which is nothing but saturation pressure. So if I go to steam table, from the steam table, I can say that PWS will be nothing but P sat from the steam table at the given temperature T1, which is 20 degrees Celsius. Okay. So how much is PWS? So if you do so from the steam table, you will be getting PWS is 0.023389 bar. Okay. Now P, what is P? Total pressure of moist air. It is given standard atmospheric pressure. So it means 1.01 bar. Calculate W, how much it is. You should be able to do it very fast now. Zero point 00. Yes, 726. 726. So 73 you can write down. Correct. Now, what will be enthalpy at point 1? This is W1. What will be enthalpy at point 1? 1.005 into T1 plus W1 into 2500 plus 1.88 into, tell me how much is enthalpy? Tell me how much is enthalpy? Do it fast. (38.52 kilojoule per kg)A. Okay, that is enthalpy. Now, because just now I have used the steam table, so this equation is considered typically the approximate equation for estimation of enthalpy. You know, na? Approximate, because we have made certain assumption that Cp is constant in steam, Cp is constant in vapor, latent heat of vaporization is 2500. I may have, because I am referring to steam table, so if I am referring to steam table, then I can also, so this was approximate. If I have to calculate exact value of enthalpy, can I calculate exact enthalpy for this case? Exact enthalpy will be what? Enthalpy of air, dry air, which is 1.005 into T1. Dry air will remain same, plus W into enthalpy of water vapor. How I can determine enthalpy of water vapor? I have temperature of 20 degrees Celsius. I will be going to 20 degrees Celsius and I will be calculating Hg at 20 degrees Celsius from the saturation table. Is this point clear or not? Because what typically is What typically is enthalpy? Dry air part plus water vapor part. Water vapor is present in the which state? Vapor state. So vapor enthalpy I can measure from 20 degrees Celsius. Is this one clear? So it will be coming somewhere close to 1.005, means this is the other way I am telling you. Other way of calculating the exact value. W1 you have already done, and from steam table you will be finding it 2537.38, and ultimately this H1 is equal to how much? 38 point again 528. So it means it is coming, the approximate value is coming very close to the exact. All are clear with this point or not? Now it's very simple. What we have? Q, simple heating is taking place. Q must be equal to m dot A into H2 minus H1. How much is m dot A? Substitute and tell me what will be H2. What will be H2? Calculate. Please do it fast. Be consistent with the units. Mass flow rate is in kg per minute, and it is in heat is in kg per second, kilowatt. Sorry, 44.528 kilojoule per kg of dry air. Okay, then I have only got now what? Enthalpy. From enthalpy, how I can calculate temperature? See, this is enthalpy. I do not have any addition or removal of moisture. So W1 will be equal to W2. Okay. Then enthalpy at point 2, I can write 1.005 T2 plus W2 into 2500 plus 1.88 into T2. I have W2, T2, sorry, I have H2 and W2. Substitute here and calculate T2. How much is T2? Quickly do it. Then let's start the next problem. How much is T2?
26 approximately.
25.89. Okay, then problem number 2, moist air enters an insulated duct at the rate of 10 cmm. Again insulated duct, 10 cmm, 10 degrees Celsius, 40% RH, standard atmospheric pressure, heated by a heater of 2.5 kilowatt capacity. We have to find the outlet state. First part is, if flow rate is given in cmm and if we assume that our humidity is, if we assume that our density is 1.2 kg per meter cube and humid specific heat is 1.00216, then we have already derived one formula for sensible heating. What was that formula? 0.0204 V dot A into simply delta T, T2 minus T1. Substitute here, get the value of T2. What is the value of T2? If you substitute in this formula, how much? 12 point?
22.
Exact value?
22.25.
22 point?
2549.
22.2?
2545.
22.25. Okay. Now, in this formula, what was the assumption if you recall? The assumption was that density 1.2 kg per meter cube I had used at under which conditions? Standard temperature and pressure. Pressure is standard, temperature was 20. Now temperature is how much? 10. And what was relative humidity in that formula? 50%. Now relative humidity is how much? 30%. Okay. So it means that this value, in this value, even if I have to use approximate formula, I need to apply certain corrections. Okay, certain corrections so that I can estimate density corresponding to. So two types of corrections I can apply. Either I can go to the original formula and then use the value of density as per the actual density which we are getting. Or second correction could be that whatever the CMM is given, this CMM is for the current condition. I can convert this CMM from current condition to the CMM value at the standard condition. Is this point clear? So better is, because this formula is given only for STP conditions, so instead of modifying its factor and then again deriving the formula, better approach is whatever the volumetric flow rate of air I am having in CMM at the given condition, I can convert this into the conditions for which formula is derived. Is this point clear or not? So how I can convert it? Please tell me. How I can convert? Again, what I need to do then, if I have to follow the exact systematic process, first I need to calculate the value of W1. Can you calculate W1 now? How to calculate W1? Relative humidity is there. The only thing is at 10 degrees Celsius, I need to determine saturation pressure. That let me give it to you. 0.01228. 1228 bar. This is saturation pressure. Now you tell me how much is humidity. How much is humidity? Please tell me. Calculate it.
Zero point zero
0.00303 kg water upon kg dry air. Correct? Now, the what will be air pressure? Air pressure will be P minus PW, which will be nothing but P minus phi into PWS. So calculate air pressure, how much it is? How much it is?
one
1.008338. If this is air pressure, can you calculate air density? What will be density of air? P equal to rho RT. So PA divided by RT. PA I have calculated, R I know 0.287, T 10 degrees Celsius, it means 283 Kelvin. So how much is density then? How much will be density? Please do calculations fast. 1.241 kg of dry air per meter cube. Is this part clear or not? Did you get this value? Please tell me, answer something. Okay. So if now at the given condition, this is the density of the air, and along with this there will be some moisture also. So that's why equivalent density of moist air will become density of air into 1 plus W, where W represents the mass fraction of mass fraction of moisture present in the dry air, unit dry air. So how much will be this equivalent density of moist air then? 1.235. 1.2448. 1.2448. Those who have class, they can read. Correct? Now, what will be mass flow rate? Density into cmm. Correct? Density into cmm. Because earlier in this formula 0.024, whatever density is being used, that is density corresponding to STP. Now we have obtained the correct density for the given condition and given cm. So if you do this, then how much is mass flow rate you are getting? 12.41 kGa per minute. Yeah, correct. So this is the actual mass flow rate. If you know the actual mass flow rate, you can also calculate enthalpy. What will be enthalpy? How much will be enthalpy? 1.005 T1 plus W1 into 2500 plus 1.88 T1. How much it is? It is 38, sorry. Yeah, how much is enthalpy? Is it close to 17.68? Is it 17.68? Okay. Then, now what I need to do? Please tell me the next step. Have I written this correct? Rho into cmm, or is it wrong value 12.41? Please check it. Is it 12.41 or 1.244? Okay, fine, no issue. Correct? Okay. Now what I will be having? Q will be equal to m dot A into H2 minus H1. From here you can calculate value of H2, which will be how much? 29.77 kilojoule per kg dry air. Now W1 will be equal to W2. Okay, as W1 is equal to W2, I can calculate that H2 will be 1.005 T2 plus W2 into 2500 plus 1.88 into T2, and ultimately from here you will be getting T2 somewhere 21.96 degrees Celsius. What was the earlier temperature? 22.25. So you can see the difference. When you go for exact analysis, then it is 21.96. When you got very approximate analysis without any correction, then 22.25, and there can be one third variant. What will be third variant? Third variant will be in the previous formula 0.024. There I can use the correct value of the CMM. Okay, what will be CMM correction there? How I can correct CMM there? Please tell me. What will be the volume equivalent flow rate of standard air? Very simple. In the previous formula, what I told you, that other approach could be, I can simply make the correction in the CMM. Okay. So, actual density multiplied by given CMM equal to density into CMM at STP. Correct? Actual density we have calculated, and actual CMM also we know how much it is. 12.41. This multiplication. This must be equal to STP density. What is density at STP?
1.2.
Into V dot A at STP. From here I will be getting V dot A at STP is how much? Calculate, quickly calculate. .3417. Okay, CMM. Now what you do? Substitute this one in the actual formula. What my point? Which formula? 0.0204 V dot A at STP into T2 minus T1 and calculate the value of T2. How much it is? It should be quick now. How much it is? How much it is?
21.85.
21.85 degrees Celsius. Now you see the differences. Whenever, without looking into the given condition, whether these are STP or not, you have simply applied the formula. What was the value? 22.25. When you did perfectly exact analysis, through exact analysis your value was 21.96. When you made correction in the actual formula, because actual formula is given for the STP conditions, what correction you made? You tried to estimate the given CMM value for the standard temperature and pressure conditions. Correct? So when you did this approximation, then your CMM value now is available for the standard conditions for which formula is derived. When you are using this, then you are getting value as 21.85, and 21.85 is very close to the value of 21.96 which is obtained from the exact analysis. Clear? So it means that whenever you will be doing the numerical problems, though we have a straightforward formula for sensible heating, even when we will be doing the system design, 0.0204 V dot A into T2 minus T1. You have to always remember that formula is derived by assuming density of air at the standard conditions, which are 20 degrees Celsius. What else? 50% relative humidity at 1.01 bar atmospheric pressure. Okay, means 1.2 kg per meter cube density. Whenever your conditions in the actual problem are given other than that, then whatever the CMM value is given, you have to correct that CMM value. And the way out for correcting the CMM value is obtain the density at the given condition, multiply, that will be the mass flow rate at the given condition. Of course, mass balance should satisfy. So that mass flow rate will be equal to density at standard condition multiplied by CMM at standard condition. From there you can make the correction. And to calculate density at the given condition, you must do this process which I have explained to you. This process. First you will be applying the calculating air pressure, then using ideal gas equation calculate density of dry air, and then using this humidity calculate density of moist air. That's it. That is the density for the given condition. All are clear with this point or not? Anyone is having any doubt? Okay, so with this now I will be stopping. We'll discuss further numerical problems in the next class.